Welcome to another episode of Numbers in Medicine. Today we'll be discussing the fundamentals of acid-base disorders. The most important reaction to bear in mind during this discussion is the following. CO2 plus H2O forms carbonic acid, which forms hydrogen ions and bicarbonate. And note that the arrows are bidirectional. So the reaction does not simply proceed in one direction, but rather both. Bicarbonate is the main extracellular buffer, and this reaction I just discussed is catalyzed by the enzyme carbonic anhydrase. One equation you will come across in your studies is the Henderson-Hasselbalch equation. And for the blood, it's the pH equals 6.1 plus log of the quantity concentration of bicarbonate over 0.03 times the partial pressure of CO2. And it's important to understand how this equation came about, because once you do, acid-base will make so much more sense. But how do we actually get the equation? First, we return to our original reaction, but let us focus on the latter half of it, that this carbonic acid forms hydrogen ions and bicarbonate. Carbonic acid is a weak acid, and weak acids only partially dissociate. And for a weak acid, we can actually write this as Ka, the dissociation constant, is equal to the concentration of the products, here hydrogen ions and bicarbonate, over the concentration of the original acid, here carbonic acid. Technically, you do this for strong acids too, but let us focus just on this particular weak acid. Now, we mentioned this is the equation for the dissociation constant, but let us actually replace it with the reaction we have in mind. And we can simply take the negative log of both sides. And the real reason we want to take the negative log is because ultimately we want to isolate for pH. So negative log of H plus is pH. Now, negative log of Ka equals negative log of that quantity H plus times bicarb over carbonic acid. Now, whenever you have things in brackets like that, it refers to the concentration of the substance. So we'll continue to isolate, use some algebra, until we ultimately reach the following equation, where pKa equals pH minus log of bicarb over carbonic acid. pKa is, as you can tell, the negative log of the dissociation constant K sub A. A low pKa indicates a stronger acid, and a high pKa indicates a weaker acid. We can prove that mathematically, but more importantly, what does that mean functionally? Typically, a pKa of greater than 3 is considered a weak acid. The pKa of carbonic acid is 6.1, so it's quite weak. And the difference between 3 and 6 is not just 3, but rather remember this is logarithmic. So going from 3 to 6 is a difference of 10 to the third, or maybe 1,000 times weaker essentially for carbonic acid. Some strong acids have a pKa that's negative. It's so low that it's negative. Those are very, very strong acids. But here we have quite a weak acid, so it only partially dissociates. Now, if we continue to do some more rearrangement, we actually end up with the following equation. pH equals 6.1 plus log of bicarbonate over carbonic acid. This looks somewhat similar to the original equation I showed you earlier, but not quite there. See, the concentration of carbonic acid is quite difficult to measure. So we actually have a surrogate marker or a replacement. Now, back to our original formula, our original reaction, the one I told you that really you know this, you know acid-base. So let's look at the first half now. CO2 plus H2O yields carbonic acid. One can use Henry's law to relate the concentration of carbonic acid to the partial pressure of CO2. Now that on its own is an entirely separate lecture. It's quite detailed. But take my word for it that you can relate the concentration of carbonic acid to that of the partial pressure of CO2 using the solubility coefficient for CO2 in the blood. So instead of measuring the concentration of carbonic acid, we say it's equal to 0.03 times the partial pressure of CO2. And with that substitution, we have our new equation, our final Henderson-Hasselbalch equation that we saw earlier. pH of the blood is equal to 6.1 plus log of bicarbonate over the quantity 0.03 times the partial pressure of CO2. Now, if we just use typical numbers to get a feel for what this equation means, we can say the typical concentration of bicarb is 24. Typical partial pressure of CO2 in the blood is 40. So if we just substitute those numbers in, we get a pH of 7.4. Perfect. pH of the blood is 7.35 to 7.45 normally. So this shows you that the equation makes sense. It works with what our physiological understanding. Now, back to this equation. With just this equation, we can determine the four major kinds of acid-base disturbances. Now, we have a better sense of what that equation means, but let's see how does changing each of the variables affect the pH. Let's say our bicarb increases. So the numerator of the fraction is increased, the total log increases, so the total pH increases. That means the solution becomes more basic, and if it's more basic, we think of it as an alkalotic process. And since we're talking about the bicarb, it's a metabolic alkalosis. Conversely, if the bicarb decreases, the fraction decreases, the log decreases, the pH decreases and becomes more acidotic. Thus, the pH decreases and we develop a metabolic acidosis. We can do the exact same thing for the partial pressure of CO2. If that increases, then the denominator has increased, the fraction has decreased, the log is decreased, and the pH is decreased. Thus, we have an acidotic process. And the way you control your CO2 is through respiration. So this becomes a respiratory acidosis. Finally, if the PaCO2 decreases, the denominator decreases, the total fraction increases, the log increases, and the pH increases. Thus, the effect on pH is inferred to increase, and this is an alkalotic process through respiration, or respiratory alkalosis. And that's really it. Those are the four major kinds of acid-base disturbances that we intuitively knew based on deriving that Henderson-Hasselbalch equation. Now, in our upcoming videos, we'll talk about some of these in more depth. You may have more than one at a time, but having this fundamental understanding is critical to truly learning about acid-base disturbances. And that is Fundamentals of Acid-Base Disorders in a nutshell.